Matthew, and he's going to talk about polymerization, in particular step polymerizations. So you'll learn a lot more chemistry. But today is meant to be a workshop. This is an opportunity, first of all, to make sure you understand some of the things that we've discussed. And you've all had a worksheet to have a go at, so hopefully you've all had a go at those questions. Is that right? Hands up if you didn't have a go at those questions. Only one of you. Oh, two of three. Yeah, a few people are admitting. Well, you won't know what's going on. But we'll have a look at the answers to those questions in just a moment. But this is also an opportunity for you to ask any other questions yourselves. If there's something you want us to go back over from the last 4 weeks. So this is your opportunity to get feedback of one sort or another, and to make sure you understand what we've been talking about. Now when it comes to an exam, there tend to be two sorts of exam questions, or two sorts of things that happen in an exam. Sometimes you're asked to explain or discuss something. So that's all about whether you've got the information in your head, and even more importantly, whether you can explain it, express it in good English, clearly and concisely, and actually answer the question that you're asked, and not answer some completely different question, as some of you will do. And the other sort is where you're asked to do something, to calculate something, to plot a graph, to actually show that you possess key scientific skills. And in the exam for this course, you should get bits of both sorts of question. Just so as you know, there will be there are three questions, or you will have to answer a question from each of the lecturers, and there's a choice. Okay, so you will have a choice on what to answer, but you will have to answer a question on each part of the course. What I teach you, what Professor Turner teaches you, and what Professor Yates teaches you. And the structure isn't the same, the exam isn't the same as last year. If you look at last year's paper, you'll see some things which we've covered, but some things which will be different, because the course changed this year. Those of you who did Chem 207-11 in your second year, if you've now got through to your fourth year, you will recognise some of the material, so some of the exam questions from that old course, if you go back long enough, would not be irrelevant. But hopefully this will be just a little bit more advanced. So the worksheet that you had was actually about the calculation bit. So it's focused on the second part of what I talked about when we were talking about molar mass distributions and average molar masses and how we measure them. And we'll have a look at that in just a moment. The worksheet didn't cover the sort of discursive type questions, but do remember that in an exam you need also be able to explain things clearly in writing. But let's have a look at the questions that hopefully nearly all of you have had a go at. And the first question was this one. You had some information. This is a question that if you go back through years of polymer exams of one sort or another, it's a popular question. Because it's really, do you understand average molar masses? Can you calculate average molar masses given some information? And you're asked to calculate the number average and the weight average of a sample. And it's a nice simple question. You've got 4 samples, you assume they're monodispersed. You're told the molar masses, 100,000, 250,000, 400,000, 500,000 grams per mole. And you're told how much of each polymer you're putting into the mixture, and given that, can you calculate the number average and the weight average molar mass for the mixture? And whenever you see a question like this, the first thing you do is you ask, how are we measuring amount? You notice that it says mass of polymer. So let's just remind ourselves of a few of the things that we've learnt on this course. We've learnt that most polymer samples we encounter are mixtures. They're mixtures of molecules of different size, different molar mass. Often they're also mixtures of molecules, even if they are chemically identical, which are different structurally. You may have branched and non-branched and so on. There may be other ways in which they are mixtures. But we're thinking about the simplest situation where we just have a distribution, a mixture of molecules of different molar mass. And molar mass is just one way, as we said, of indicating the size of a polymer molecule. We've talked about many other ways. And as we've said, when we talk about a technique like gel permeation chromatography, the separation isn't directly on the basis of molar mass, it's on the basis of hydrodynamic volume. So you need to find a way of converting from that size parameter to molar mass if you want to know molar mass information. We talk about how we can do that using a calibration or using other detectors which actually determine the molar mass. Now, if we're thinking about a distribution, a mixture, we need to know not just for each possible molar mass or possible size, we need to know how much have we got of that size. And this is the key thing to remember. We can express amount in different ways. And most of the ways which we express amount either relate to how many molecules or how many moles of molecules we've got, it's a number term, or that relates to what mass of material we have, what weight of molecules we've got altogether in that size range. And we always want to keep in our minds, be aware, are we dealing with numbers or are we dealing with weights? And as we said, there's nothing unusual. When we go to the supermarket, we routinely slip between counting things out and weighing things out. It's not a problem for us, and it shouldn't be a problem for us here. We've got some expressions for numbers, average and weight average molar mass. And we've got expressions both in terms of numbers, n's or number fractions, something like that, or in terms of weight, w's, weight fractions, something like that. So we can work out our averages for any situation as long as we bear in mind, are we dealing with the number term or the weight term? So in this particular question, are we thinking in terms of numbers or weights? We've got our molar masses, and we've expressed amount in terms of the mass of polymer. We've got 3 grams of the monodispersed sample of molar mass, 100,000 grams per mole. We've got 2 grams of the sample as 100,000, and 1 gram of each of the other 2 samples. So we're thinking in terms of W's, not N's. These are our W, we can call that WI. We can call anything proportional. We could divide through, if we had that up, 3, 4, 5, 6, we could divide through by the total and do it as weight fractions. We could multiply it by anything. It's the proportions which matter. As long as we're self-consistent, it doesn't matter what we call W as long as the ratios are the same and we work things through logically. So if we're dealing with W's, then those are the expressions that we can use. The number average is the sum of all of the weights divided by the sum of what you have if you take each weight for each component and divide by the molar mass of that component. The weight average is the sum of the weight times the molar masses divided by the total weight. So once we know we're dealing with W's, it should be easy to work out our answer. Because the things we need to know, we've got our W's, we need to know our WI divided by MI, we need to know our WI multiplied by MI. So WI divided by MI, oh hang on, let's add up everything first of all. Our sum of the weights is 7. We could, if we want, divide through by 7 and get weight fractions and then follow it through. It doesn't matter as long as we're self-consistent. If we leave the numbers as they are, then we've got 3 divided by 100,000, that's easy. 3 times 10 to the minus 5. We've got 2 divided by 250,000. That should give us something like 5.7 times 10 to the minus 6. We've got the reciprocal of 400,000, 2.5 times 10 to the minus 6. We've got the reciprocal of 500,000, 2 times 10 to the minus 6. Those are our WI divided by MIs. Add those all up. And if I've done my sums right, I hope someone's checking this. If I've got it wrong, tell me. It should be 4 times 10 to the minus 5. Now, you've all done this. We should be just checking your answers that you've already had a go at. If we look at what happens if we take WI and multiply it by MI, 3 times 100,000, that's easy, it's 300,000. 2 times 250,000, that's 700,000. Then we've got 400,000 and 500,000. Add up all of those, 1.9 million. So now we've got all the information we need to calculate our averages. Our number average will be the sum of the WIs, that's 7, divided by the sum of the WIs of 1 MIs, that's 4 times 10 to the minus 5. The weight average will be the sum of the WIMIs, which is 1.9 million, divided by the sum of the WIs, that's our 7. And so you should have got 175,000 or thereabouts for the number average, 271,000 or thereabouts for the weight average. Hands up if you got that right. Well done. It's easy, isn't it? But it's amazing how many of you in an exam will get muddled. You'll think you're dealing with numbers when you should be dealing with weights or something like that. Remember in an exam, you know, these calculation questions, if you get calculation questions, they're the ones you should really know. Because they're the ones you can easily get full marks for. If you're describing something, you've got to really do well to get full marks. But calculations, if you get it right, you've got it right. And so you should all be getting full marks for something like this. And the only reason you don't is because when you're under stress, when you're in an exam, you will make mistakes. We all make mistakes. We know we're going to make mistakes. So you train yourself when you're under stress to stop and check things. And there are some simple things you can check. You know, for example, that the weight average will always be bigger than the number average. If you've got these the other way around, if your weight average came out at 175,000, your number average is 270,000, you'd know you'd made a mistake. So you go back and check and get it right. Then you can get your full marks. Just train yourself to look out for the little things that enable you to test whether your answer is reasonable or not. You can look at the data you've got, and you can be pretty sure, pretty sure that you're, this is in terms of weights, you're weighted, you've got a lot at the low end, so your weight average more mass is going to be somewhere around 300,000. If it came up as 6 million, you'd know you'd made a mistake. So again, check your answers. Train yourself to check your answers, because that's the way to catch the mistakes, and that can make the difference between full marks and not many marks. Okay, you then had another question. Got the same mixture, well, the same components you're putting into the mixture, but remember in that first question, we were dealing with weights. Now we're told we have the same ratio, but now it's by mole. So now we're going to work things through with a different way of expressing amount. So now, you've got the same numbers, but now the 3211 is an N, not a W. And we've got our expressions for number average, molar mass, and weight average, molar mass. Now we want them in the terms which use N's rather than W's. So our Nn is now going to be the sum of NI divided by the sum of Ni. Our Nw is going to be the sum of Ni times the square of Mi divided by the sum of NiMi. So now we know what information we need if we're dealing with moles rather than masses with weight. We know what information we need to calculate those averages. We've got our Ni's, we can add them up, 7. If you like, you can divide by 7 and have a number fraction. It doesn't matter, as long as you're self-consistent, you'll get the same answer. You could say 300, 200, 100, 100 if you like. It doesn't matter as long as the ratios are correct and you're self-consistent in what you do subsequently. And we need our Ni's times Mi's, so we can... we've already done the sums, except last time there were Wi's times Mi's. So we've got 300,000, 700,000, 400,000, 500,000. Add them up, 1.9 million. And then we want our Ni's times Mi's. We want to multiply each of those by n again. So we've now got 3 times 10 to the 10, 2.5 times 10 to the 11, 1.6 times 10 to the 11, 2.5 times 10 to the 11. Add them all up, we've got 6.9 times 10 to the 11. Now we've got all of the information we need to calculate our averages. Our Mn this time will be 1.9 times 10 to the 6 over 7. Our Mw will be 6.9 times 10 to the 11 over 1.9 times 10 to the 6. You should have got Mn now is 271,000 grams per mole. Mw is 363,000 grams per mole. Hands up if you got that right. Well done. But why are there some hands not going up? Did you notice something? You've seen that 271,000 before. Because if we go back, that's what we got for MW when we were working with the W's. And it has to be because of the relationship between these averages. In other words, if we're working with W's, what we get as MW is what we get as Mn when we're working with numbers. That's a mathematical necessity. I remember when I was in industry, you know, after I worked for BP for a few years, and one thing we were doing was characterising polymers. And we were actually doing GPC for a subsidiary. This was BP. At that time they had a big chemicals industry that they've sold off long ago now. And they were actually using refractive index detector and a UV detector. And they were getting different answers. And then they noticed that actually the Mn for one was the MW that they got from another. And we realised what was going on. This particular polymer, it was a HIPSO, it's a polyisobutene with a silicon hydride end. It had a UV chromophore just on one end of the chain. So the UV detector was detecting a number distribution, whilst the refractive index detector was detecting a weight distribution. So if you apply the equations to what the UV detector was doing, as if it were a weight distribution, you actually got the numbers wrong. But there was this relationship between them. So you could immediately tell. It took actually, you know, these were people who did polymer characterization. It took them a while to work it out, what was going on actually. It shouldn't do. If you actually understand the difference between numbers and weights, it should be obvious. Okay. If you get a question like that in the exam, you should be laughing. Ah, it's easy, I can do that, no problem. These are all questions which have actually appeared, at least as a bit of a question, in some exam or another at some time. Sometimes at master's level, sometimes at second year level. The problem is you always have to start out in the same place. But they've all appeared in exam questions in exam papers in the past, in different courses. Okay, this one is about GPC. And this is a nice, simple one. If you get one this simple, you'll be really lucky. It might not be quite as simple as this. Again, this is an example of where you're told something that might, you know, this could be real data that you're getting. 10 samples of polystyrene with narrow molar mass distributions. These are the sorts of standards which are used for calibrating a GPC column. They're put through a column, and we've got a whole range of molar masses. Polystyrene standards are available over an enormous range. They're prepared by anionic polymerization. They tend to have narrow molar mass distributions, MW upon Mn, perhaps 1.02, something like that. And here we've got the elution volume at the peak. So we're just focusing on, these are narrow samples, so we're just focusing on the peak. We're not calculating any distributions or anything here. And you're asked to use the data to construct a calibration curve. Now remember, our conventional calibration in GPC is a plot of the logarithm of molar mass against dilution volume, because that generally gives an approximately straight line relationship. So what we need is the logarithms, and we usually plot it as logarithms to the base 10, and I've been very good here. I've quite correctly actually expressed it as log 10 m upon grams per mole, which I should do if n is a molar mass, because remember, a logarithm has to be dimensionless. You can't log units. So whether we explicitly write it down or not, whenever we take a log, if we're dealing with something with units, we're actually dividing through implicitly by the units. So we've now got some log n values, we've got some elution volumes, and then we can plot log n against elution volume, and we see something like this. We realise that a t gen there are samples which aren't being differentiated, and we have a separation in the middle. And you notice that the question has an extra bit, so this isn't all about calculation. There's also some explanation. It says, explain the shape of your curve. Don't miss out bits of this question like that. There are useful marks there. Again, it's amazing how often in exams people miss out, they just don't answer bits of the question. And so they lose marks. You don't want to throw marks away. Just check that you've answered everything that you're asked to do. So here you've actually got to show that you understand what this is telling you. So what are you going to talk about? Well, in the middle we have a region which is actually quite remarkably linear. This is artificial data. It's very rarely you would have a GPC calibration which is actually that good straightest line over all of the range. But essentially we have that more or less linear relationship we talked about between log m and elution volume. But it's only within a certain range of elution volumes. Because remember, if GPC is functioning as it should, everything will emerge between two limits. It's not like conventional liquid chromatography, where you just wait, and if necessary you wait for days for something to come out. In GPC, if it's working as it should, if you have a genuine size exclusion mechanism operating and no absorption, no interactions with the column, then everything should appear, and if no other mechanisms like hydrodynamic chromatography are occurring, then everything should appear within a certain range of elution volumes. And we have that range here. So, very large molecules, once we get above a certain size, everything elutes at the same relatively small volume. Remember in GPC, the biggest molecules come out first. We talked about why that was. Okay. So very large molecules elute at some volume, which we can associate with the void volume of the column. That, if you remember, is the amount of space which is between the porous beads, not inside the beads, but between the beads in the column. So that gives you something to talk about, to discuss, to show you that you understand what's going on in a GPC column. And at the other extreme, again, we stop getting any separation. Because once we get below a certain size, all of the molecules elute at a volume which corresponds to the total volume, the void volume, plus the internal volume. That's the volume of solvent that's contained within the beads, in all the little pores, the spaces inside the porous beads in the column. So there's a lot you can discuss here. This is an opportunity for you to show that you understand the mechanism of separation in GPC. Okay. You're then told that there were 3 further samples of polystyrene analysed using the same column under the same conditions. And this is really easy. We've got 3 elution volumes. What are the molar masses? We're not calculating distributions. You don't have to worry.
From the graph, we have a point which is outlined at the volume of 32.7. And the graph shows that on the right. How will that explain?
Sorry, say again.
This point to
yeah.
This point also on the graph
It shouldn't be an outlier. Just double check. You said you've got an outlier. What point are we talking about?
5.7 times 10 power 4. The fourth value from the bottom on molar mass. When you get to the row, it's not 4.76.
28.5, 32, sorry, 32.7?
32.7 volume, yeah?
Yeah. And then it goes up to 35.3.
The molar mass, which is 55.7 times 10 power 4.
Yeah.
When you get to the row, it's not 4.76. It's
4.7.
Give 5.76.
4.76. Everybody else gets 4. I don't know what your calculation is, but everybody else gets 4.76.
Yeah. It's power 4 and power 5.
So that's another one.
It's power 4.
So if you've got one point that's way out, go back and just check you've done your sums right. It might be I've made a mistake, but it might be that you've made a mistake. You've keyed something wrong into the calculator or something like that. Okay? So I think you should find that, you know, that point is almost at the void volume. It just is that we're talking about that point there. But if you calculated the 5.76, it's going to be up here, and that will really confuse you. Okay, so where have we got to? So we've got 3 new samples. We know the elution volumes. We're only asked about the peak molar masses, so you're not even asked to calculate any distributions or anything complicated. This is an easy question. Sometimes people think questions are more difficult than they actually are. So look carefully at the question. Okay? So we've got 3 elution volumes. Once we've got our plot, if we've drawn it nicely, remember in an exam you always have graph paper available. And if you want to get information off graph paper, use the full size of the graph paper, choose your axes well, so you don't have sort of one little tiny corner of the graph paper where everything is, you're trying to measure everything. We can read off our log n values, and in this case then we should find that your molar masses were something like 300,000, 200,000, 100,000 grams per mole. That's a really easy GPT question. That was a conventional calibration. Okay. But of course you could have been given more complex information. Okay? So here if we're just doing polystyrene, that's fine. But what happens if we have a different polymer? Okay? So you might have been given information about elution volumes, but also intrinsic viscosities, or K&A values, which would enable you to calculate intrinsic viscosities. And you might have been asked not just to do a calibration plot, but to do a universal calibration plot. And the chances are, what is going on here? And the chances are that because we are trying to help you, and we don't want you to make a mistake, we might well have written universal in bold, underlined, so you don't miss the fact that it's a universal calibration, and still 20% of you will give us a conventional calibration. Read the question carefully. Actually, often more than 20% of you. Make sure that you're answering what's actually being asked. Okay? Because you know, if it's a universal calibration, instead of putting log of m, you might be, depending on what information you've got, if you've got intrinsic viscosity, you would take m multiplied by intrinsic viscosity, plot log of the product of intrinsic viscosity and molar mass. Or if you've got K&A values, you might express it as log of all of Km to the 1 plus A. It's all in your notes. But look carefully at any question that you're given. If it's about calibration, are you being asked to do a conventional calibration, log m against solution volume, a universal calibration? We try to make it clear. It'll be written there. Sometimes we try to make it very clear, bold, underlining. And I'm not kidding when I say that many of you will ignore that. However we try to make it clear, capitals. You know, we can't on an exam paper have sort of little flashing neon lights saying, look at this word, this is important. But we do our best to make the question as clear as possible. And if you don't answer the question that you're actually asked, you're not going to get the marks. Right, the fourth question. Any problems, any other problems with those first 3 questions? They weren't difficult, were they? No. Again, this is a question about if you're given some real data, can you actually manipulate it and get a real answer out? And we've read it nice and simple, only 4 concentrations. This is capillary viscometry. Okay? it happens to be polyacrylonitrile and dimethyl formamide at 30 degrees centigrade. It could be something, you know. We've got information for 4 concentrations. We've got the concentration and the flow time. Remember that to analyse the data, we need a flow time for solvent. In this case, it's mentioned there at the top. The flow time for pure solvent was 200 seconds. Of course, if we had written a table with an extra column, where the concentration it said 0, you know, 0 concentration of polymer is pure solvent, isn't it? So the number there would be the flow time for pure solvent. I do remember an exam in which the question was phrased that way. And some of the people who set the exam complained that we hadn't given them the flow time for pure solvent. Yes, we had. It was there. But they hadn't noticed that 0 concentration means solvent. So look out. You know what information you need. It should be there somewhere. So you're asked to evaluate the intrinsic viscosity, sometimes but not often equals the limiting viscosity number of this polymer in this solvent at that temperature. Remember, intrinsic viscosity depends not only on the polymer, it depends also on the solvent and the temperature. Change the temperature, it changes. Change the solvent, it changes. At least a bit. So here's our data. What information we need. Remember that this is all about relative viscosity. We never actually calculated actual viscosity here at all. Our relative viscosity, we assume, is the ratio of the times. We're ignoring any other corrections we might have to do. So we're going to take 245, divide by the time for pure solvent. Remember, we had that back in the question, 200 seconds. So 245 divided by 200, 1.225. If I've done my sums right, someone tell me if I've got it wrong. 295 divided by 200, 1.475. 350 divided by 200, 1.75. 410 divided by 200, 2.05. Are these right? Yeah, you all agree? Good. Once we've got that, it's very, very easy to calculate the specific viscosity. Remember, there's no complicated maths here. All we're going to do is to subtract 1. That's not a difficult sum. So you've got 0.225, 0.475, 0.75, 1.05. But remember what we plot, because we're looking, remember, we've got a concentration dependence, we're looking at what happens at effectively 0 concentration. So we have to extrapolate to 0 concentration, or what's sometimes called infinite dilution. And there are 2 plots we can do. One is we can take our specific viscosity and divide that by concentration. So we've got 0.225 divided by 0.002. Remember, our intrinsic viscosity will end up with the reciprocal of whatever units we use for concentration. So if we leave the concentration as grams per cubic centimetre, our intrinsic viscosity will end up in cubic centimetres per gram. So 245 divided by 0.002, we've got 112.5, and then we've got 118.8, 125, 131.3. And then we can also take, just as a double check, the natural logarithm, log to the base c, of the relative viscosity, and divide all of that by concentration. And if I've done my sums right, one would have 101.5, 97.2, 93.3, 89.7. Is that right? Other people got the same thing? Some people are nodding. Good. So now we've got all the information we need to calculate what we want twice over. So we can double check. We plot the data. The blue circles are the data for specific viscosity divided by concentration. The red squares are the data for the natural log of relative viscosity, all divided by concentration. And if all works well, they should extrapolate to the same point. They don't extrapolate to quite the same point. Real data never does. It's always a bit of error in there. But they should be reasonably close. If they're way out, there's probably an error, a mistake somewhere. So that's the point. You go back and check your sums. But they get reasonably close to each other. If anything, trust the top line rather than the bottom line. So our intrinsic viscosity is something like 106 cubic centimeters per gram. Is that what everyone got? Hmm? Yeah. Okay. There's a okay, 106, 110. Within the error you can see, well, actually 110, that seems a bit high. Okay. So the question here is about rounding, and this is an important point. Let's just go back to our table here. How many significant figures are we dealing with in the data? Okay, so when you have some data, you want to work it through with at least as many significant figures as the most precise bit of data that you've got. But then you have to make a decision at the end of the day as to what is the likely precision of my answer, and present your answer accordingly. Now, it's always a good idea, if anything, to work things through with a little bit more, with one more decimal place, one more significant figure than is really justified. Because otherwise you can start introducing rounding errors at an early stage. Do avoid the trick that some people do, that they put everything into a calculator and they quote their answer with about 10 decimal point places. You know, that examiners don't like that, because that shows you're not thinking about what you're doing. But in this case, we've got our time, 245, that's 3 significant figures. Concentration, we've got at least 0.002. We could argue for 3 significant figures at least. So what I've actually done, I've said, right, let's work it through with 4 significant figures to try to make sure I keep all the precision. There's no point putting an extra figure on that, because that would be meaningless. But then I've quoted the final answer to 3 significant figures, because that's the most that is justified on the basis of the data that you've been given. So, but if you round too much at this stage, then you're going to introduce extra errors, and if you're not careful, you'll come out with an answer with plots which are much more scattered and an answer which is perhaps fairly different. Now, if it's reasonable, you'll still get most of the marks. But try to keep the precision as long as possible. Don't round too much too soon, but equally don't waste a lot of time with lots of odd decimal places that really don't mean anything at all. So in this case, I would work it through with 4 significant figures. That last figure isn't really significant, but it just keeps the precision by keeping it there right until the end, when you get your final mark, the final answer. So you should get it anywhere between 100, probably about, certainly anywhere between 100 and 110, you'd probably get almost full marks. If you're way out, much out of that, then I think there's something's gone wrong somewhere. That wasn't quite the end of the question. It says, calculate the viscosity average molar mass for the sample, given that the mark parameters for polyacrylonitrile and dimethylformaldehyde at 30 degrees centigrade are. Now this confuses some people, because I'm being correct and say, by pointing out that the molar mass you get will be a viscosity average. This is not like the first questions 1 and 2, where you were told about the components of a mixture and you had to calculate the average. This is an exercise in applying the Mark-Hui equation. In other words, to take your intrinsic viscosity and come up with a molar mass, and what you know is that that molar mass will be a viscosity average, and you have been told how that's defined, but you don't have the information to calculate it otherwise. So here are our K and A values. K is 37 minus 3 cubic centimeters per gram. Note the units. Make sure that the units you're using for K are consistent with the units that you have for your intrinsic viscosity. If your intrinsic viscosity is in different units, say deciliters per gram, then you're going to have to do a conversion, because the units of intrinsic viscosity appear in that K. So look carefully at the units. A, of course, is dimensionless. It's just a number. It doesn't have units. So our Mark-Hui equation is a very simple one. The intrinsic viscosity is K. times m raised to the power n. We're told what k is. We're told what a is. You've just worked out what your intrinsic viscosity is. So the question is, can you reorganize that to get m? So then, we're going to divide through by k. So m to the a equals intrinsic viscosity divided by k. Therefore, m is intrinsic viscosity divided by k, all raised to the power of 1 over a. So we take out 106, now 13 times 10 to the 3, and now 0.74. You should have come up with an answer something like, I've only quoted it here to two significant figures, because that's what we've got in our A. Well, you could quote argue for three significant figures, but they're about, it should be about 62,000 grams per mole. Get that? Yeah, some people did. That was easy, wasn't it? Yeah. No difficulties. Now, we've still got a few minutes if you want them. Anything else you want to ask about? This is your opportunity. Anything you want us to go back to or discuss? Or are you just desperate to escape? Had the opportunity. I think you're desperate to escape. Okay. Thank you for being a good class. And